So, hello, dear students, and welcome to lecture 2, part 3. So, after part 3 and part 4, just to inform us, we're going to be having a series of questions on the USEM for us to answer and prepare ourselves for the midterms that's just around the corner. So I advise every one of you watching this video at this point in time to go back on lectures 1, part 1, part 2, part 3, part 4, and lectures 2, part 1, part 2, part 3, part 4, because that is all that it is that will be covered in the exercises that are going to come afterwards on USEM, and then the midterms that is coming your way very shortly. So prepare yourselves for that, and let's get right into the lecture. So we're going to continue from where we stopped, and at this point in time we're looking at molecules and ions. So we said molecules are basically a combination of two or more atoms combined together to form a molecule. And notice that the combination is of non-metals. What is combining is non-metals. And when non-metals combine, they combine to form covalent bonds, not ionic. Metals and non-metals, ionic bond, but covalent bond is non-metals. And then the force that holds them together too, there's a strong force that holds them together, and we're going to talk about that earlier, or shortly, sorry. So that's what we call molecules, which are a combination of two or more atoms. Notice that compounds are a combination of elements, two or more elements, but molecules, two or more atoms. And that's what we call molecular formula. Notice that anything that is called formula is a combination of letters and numbers. When you see formula, almighty formula, different formulas that we have in the mathematical realm or the physics realm. So you have molecular formula. So this is the number of each atom, and it's indicated with this subscript. Subscript. So you have what we call a molecular substance. So now there's a molecule, there's a molecular formula, which is the formula for the molecule, and then there's a molecular substance. So an example is water. Is a molecular substance, and then this is the formula. So this is the molecular substance water, and this is the formula, molecular formula. So that's how it works. So we have what we call structural formula. Anytime you hear the word structure, it has to do with a structure. So if you see a table, you know it's a table because of the structure that you can see. If you see a chair, you know it's a chair because of the structure that you can see. So the structural formula actually shows the bonding patterns within the molecule. So on the slide you can see how oxygen bonds to hydrogen, how the oxygen still bonds to another hydrogen, and when you look at that, you know that that's a water molecule. You can see this molecule here. How many of you know what molecule this is? How many of you know what compound this is? When you see hydrogen, another hydrogen, it's ammonia. So let's go to the next one. You see a carbon bonded to a hydrogen, one hydrogen, another hydrogen. What compound is that? And by the way, this is ammonia gas. This is also a gas. You guessed right, methane gas. So that's also another gas, methane gas. This structural formula shows you the different bondings, and notice they are covalent bondings. So you have what we call condensed structural formula. It's still structural formula, but this one now is condensed. Think of anything that's called condensed. It's something that's put together. So this one suggests the bonding pattern highlighted presence of a reactive group of atoms. It can be called reactive group, or it can be called functional group. The reactive group and functional group. And the functional group is the part that tells you the name the family belongs to. It's almost like your family name is constant, but your personal name can change. So you can have methyl, ethyl. I think methyl is the first member of the family. Ethyl is the second member. Propyl, butyl, pentyl. You have them just going on like that. And then the alcohol is the family. So this is the alcohol family. So what tells you this alcohol family is the OH group, and the attachment to the OH group is what changes. This is what changes. So this is methyl alcohol or methanol. Any of the names are correct for this. And notice that is the methyl group that is attached to the OH functional group. And in this other case, you have the methyl group attached to the amine functional group. I hope that is clear. Then now and by the way, those models that we saw previously that we're pointing at was the ball and stick model. On there we can see the space filling model and then the ball and stick model. Notice that the ball is attached to a stick and attached to another ball. Notice that most of the times the color codings are consistent. Anytime you see red, oxygen. Anytime you see blue, nitrogen. Anytime you see black, carbon. And it's no accident that the color coding is that way. Carbon is mostly your wood structure. If you burn wood, what color do you get? Black. The ocean is rich with nitrogen. Notice that when nitrogen is a little bit more concentrated, you have them a little bit above, and in the sea, notice it's mostly bluish. And then oxygen. Anytime you think about oxygen, you think about the blood, red. So you have the ammonia molecule, ball and stick model, spill film model, the same. Ammonia, the space filling model of ammonia looks like this. The ball and stick model looks like this. Methane, space filling model, ball and stick model. So you have an example or exercise that you should do. So the question is, give the molecular formula of 1 ethyl alcohol. This is the elder brother to the methyl alcohol. So notice that what is changing now is an increased number of carbon, and as the carbon increases, the hydrogen also increases, but know what is consistent is the OH at the side. So notice that now is how many carbons do you have there? Okay, let me not give you the answer. Just write the molecular formula and then continue. Pause the video, write the molecular formula, and then get back to it. Simple. Just write the number of carbons you can see. Height C, number of carbons. H, number of hydrogen. O, number of oxygens. Let me just give you a off. But I've given it enough. I've given a lot of. Okay, so I guess you have done it already. Straightforward. Let's just go right into it. So you given the information given the structural formula, and they give even the molecular substance, the name. So you asked to give the molecular formula. So what you do is add up to form the subscript. And I told you anything that is subscript is under and the figures. So number of carbons 2, number of hydrogen 6, number of oxygen 1. Notice that you don't write 1. I think some of the students are always tempted to write 1. I said, look, If it's 1, we can see it. If it's 2, you have to tell us. And if it's 0, it will not be there. So you don't go writing 1 after oxygen. It's very wrong. So you go down and you see ethylamine, C2, H7, because amine has 2 hydrogens and then nitrogen is 1. So all of the molecular formula gives you the composition of the molecule. They reveal nothing but the way the atoms fit together, so they are more or less useful than the structural formula. So how we call the ions? So we've dealt with molecules, now we're looking at ions. So when atoms or molecules lose or gain electrons, you have that ionic situation. So they form charged particles, which are called ions. So it's the losing or gaining of electrons that gives you ions. So depending on how the loss happens, it can be positively charged and you call them cations, or it can be negatively charged and then you call them anions. So it's gain or loss. So when sodium gains, when chlorine, you have all of the situations. So there is no change in the number of protons in the nucleus when an ion is formed. So remember that the change cannot happen to the protons because the protons are present in the nucleus. The change can only happen on the electrons. That's why we use the protons as the atomic number, because change cannot happen easily to that. So let's get right into it. We have an exercise since we understand. So scandium is a transition metal and it is now added aluminium to create an alloy. Remember what they said alloy is. An alloy is an homogeneous mixture of solid materials where you have your metals mixed with another metal. You don't call it a solution, because a solution is a mixture, homogeneous mixture of the solute and the solvent to give you a solution. And then the alloy now is two metals, and the idea of the mixing is to form a metal of a higher quality. So, and this is what is used for your aluminium bats, to make the aluminium stronger, because it's a bat. You don't want the bat breaking on you when you swing it. And then the bicycle frames, it's holding the tire, so you don't want the frame either bending or something like that. So they makes it stronger. So they say we should determine the number of protons, neutrons, and electrons. By now, you should be able to do that off the top of your head, because we know what the number of protons are, just given the nuclear symbol. And this time the nuclear symbol has an added value which shows us the charge. So my first question is, that a cation or an anion? Yeah, is it a cation or an anion? Choose one of them. Okay, you get it right. The cation. It's not an anion. It's a cation, because you see plus. It's cation. I told you, cat, positive feeling, positively charged, cation. Negative, I say when you write AN or AB or A in front of something, it becomes negative. So that's negatively charged when you have AN, anion. So now the question is, what's the number of protons? Okay, so the number of protons, obvious from the symbol. You know it. What's the number of neutrons? This is where you subtract one value from the other value and get it, which is obvious. And then what is the number of electrons? So you do the maths with the number of protons and you get that. So I'm giving you a lot of clues. You can try to solve it, pause and try to solve it, and then I'll answer it now. So we know your your Z, which is the one beneath, is your number of protons, and then your A is the combination of protons and neutrons, and then your electrons is your protons minus your charge. So at the end of the day, your Z is your 21, then your E is your 21 minus plus 3, which gives you 18, and then your A is your combination of neutrons and your protons. So to get the answer, you have to do 45 minus 21, which is 24. So you have everything you need, and that is it. So now we're going to look at monatomic and polyatomic ions. So remember, we said ions are positive or negative charge. Now we are looking at ions on the basis of the amount of elements that are present, or the amount of atoms that are present. That's why it's called monatomic, meaning that these are ions derived from a single atom on the basis of loss or gain of electron. And then the polyatomic, these are ions derived from more than one atom. So on the basis of gain or loss from one or more, from a atom that has more than one, for atoms that are more than one, you call them polyatomic, because poly is many, so it's more than one. But for one, it's monatomic. So you have examples for monatomic. Sodium is just one, and it's a cation. Chlorine is just one as well, one atom, and it's an anion. And then you have the polyatomic. You have hydroxide, is both oxygen and hydrogen, and it's an anion. And then you have ammonium ion, which is a cation, and it's a combination of 4 hydrogens and 1 nitrogen. So you see the example, the image here, see what it looks like, and notice that they're covalently bonded. And then you see the charges. You have to include the bracket and put the charge at the side. Very important. So this is an ionic compound, and the ionic compound, basically, remember we saw monoatomic ions. So we say when things bond covalently, the bonding is carried out by nonmetals. And remember, when nonmetals are on the periodic table, and they're close to themselves, so hence they share electrons, because covalent. Sorry, I forgot to ask this question. Covalent bonds are bonds, and they involve sharing, and it's done by nonmetals. And I jokingly tell students all the time that covalent bonds are it's anything that has in them has to involve sharing. And then students, I tell them, I say, can bring up anything that has in them, and I'll tell you how sharing is involved in and then students will say Coca-Cola. And then I think a student actually then told me that was Coca-Cola, and then I said, even in Coca-Cola, the theme for Coca-Cola is share the enjoyment. So you see, you'll find sharing somewhere in anything that has because if you think of a company, they're either doing something that they share with people, and they are even sharing spaces with themselves. And there's a whole lot of things around about that you always will find something. Even the Coca-Cola is a combination of sugar, cola, water, and all of those things, and they share the one bottle together, and then you're sharing it with someone else when you buy it, or buy it for yourself. So Ionic is different, because Ionic now has metals and non-metals coming together. Notice that sodium is at one end of the periodic table, chlorine is at the other end of the periodic table. This one gives, the other one receives. So that's ionic. But with covalent bond, they are on the same end of the periodic table and they are close to themselves. So because they are not far away, it's not ionic where transfer is what happens for ionic. They transfer electrons. But with covalent, they share because they are closely locked to themselves. So they share. So I hope it probably makes sense. In the future we'll dive more into it. Now look at this. This is why salt has a crystal structure. Just to explain, we had done this previously in the first lecture, but just to make it make sense, look at this very closely. You have your chlorine molecules. Notice the color coding. I told you nitrogen is blue, right? But this is not blue for sodium because it's Na. The color is not blue. Look very closely. The color is not too good with all those shades of color that are close to it. Almost like it's purple. It's almost like it's a shade of blue, but it's not blue. Blue is nitrogen. When you see blue, you know it's blue. So the color codings are quite specific and unique. So I told us green is chlorine, and chlorine is a greenish yellow gas. So notice that the color coding is very related to the actual color it is, in a sense. And by the way, for blood, notice that what gives blood is actual color is iron in the hemoglobin. That's what gives it its actual color, but because it carries oxygen, because it's a combination of hemoglobin bonded to oxygen, that's why it's. I'm sorry for going all chemistry or biochemistry on you. So just to give you clarity on what exactly it is. So forgive the twitching that happens once in a while. It's because of the colors I'm using on myself. So it's a filter. Okay. So going by this, what you have is a chlorine molecule locked into the sodium molecule, and this is what gives it its crystal structure. So salt has a crystal structure on the basis of this interaction, and that is why when you put salt in water, the water molecules envelopes the individual chlorine and sodium molecules, and that's why the salt disappears in water. Does it make sense? Because this is a crystal structure, and on the basis of its crystallinity, it is dissolvable, not as easy as something that is covalently bonded. It will make sense when we look at conductivity. You will now understand why salt conducts electricity when dissolved in water, and salt solution. So we have an understanding that forces act between ions. There are forces acting between, the same way you have a force acting between or acting on about a magnet or between bars of magnet. So when you put a north pole and a south pole, it will attract because there's a force. When you put a north and a north, it will repel because there's actually a force that causes the repulsion. So ionic compounds are held together by strong forces called ionic bonds. So the bonding is as a result of the force. So the strong forces called ionic bonds. So they cause an attraction between positive and negatively charged ions. So there's an attraction. This bonding, ionic bonding forces are what causes it. So compounds are usually solids at room temperature. So they have quite high melting points, or they can be water soluble as salt is. So those things are water soluble because of the bonding. When water molecule comes in, because of the nature of water molecule, the hydroxide, which is negatively charged, and the hydrogen, which is positively charged, they tend to envelope and pull apart. That's what makes them soluble in water. And then the high melting point is when you're trying to use heat. It's difficult for you to dislodge them with heat easily because they are ionically bonded to one another. Solutions of ionic compounds. So when an ionic compound dissolves in water, the presence of ions in the solution leads to electrical conductivity. Electrical conductivity is simply the conduction of electricity on the basis of the ions present in that particular solution. So when you have salt and water, notice that the salt doesn't just vanishes, it's just broken down to its individual ions. That's why you see this whitish cloud with salt. And to some of you that probably are new to the island, and you probably have been wondering why sometimes when you take a shower your body is itchy. It's the salt in the water that most times gives foreign students a hard time, especially if you're not used to salt in the water and you showering it. Even though the salt is not there or there's very minimal, because the water that we have now is very fresh, is the one gotten from Turkey. So but for some foreign students that have sensitive skin, just notice that what causes the problem. So and most times you've experienced that when you run to the bus stop and then your body needs to sweat, but your sweat pores is blocked with the salt in the water, very tiny particles of the salt that couldn't effectively dissolve, and then it results in itchy because your skin wants to give off sweat but it can't because it's blocked. Then you start itching yourself. Just to help some international students that will probably be having issues, because we're talking about salt. So notice that the strong electrolytes are basically what is gotten from the basis of the solution. So it conducts electricity, and we'll see why it does. I've explained it, but we'll see it in some imagery. So when molecules of solid dissolve in water, and this molecule of solid will probably be covalent, so no ions are formed, and without the ions, the solution cannot conduct electricity, so they are non-electrolyte. That's why from the example that we'll see here, you have just water. Solution of pure water does not contain ions, and thus does not light a bulb. So when you have water, and there's some water that can have some ions in them, on the basis of the purification methods that's used, because sometimes you can have residual chlorine in water because the water was treated with chlorine, and that sometimes might give off a little bit of. And then the next part, you have water that a solution that sugar is put it out, table sugar, which is called sucrose. You have glucose, you have sucrose, you have fructose, which is sugar from fruit. And when you dissolve that in water, that is a combination of covalent bonds, so it doesn't conduct electricity. But when you have salt, as a table salt in water, notice that it has the tendency to have ions that will enable conduction of electricity or conductivity. So as you can see, it lights a bulb. And let me just share this. Back in my high school, when we used to have all those batteries, those batteries that have the rod inside them. So the little chemistry we do is when the battery dies and we don't have a means to get a new battery or the market and all of those things, we have issues, and maybe it happens in the night and you can't get the shops. So the little chemistry we do is we pull out the rod of those batteries, those funny looking torchlights, those big batteries, those brands of bicycles that allows you to take away the plastic cap and pull out the rod. Then we put some salt, put a little bit of water, and then inside the rod put it out so that the salt moves around a little bit around it. Then we put it, and then we inside the battery is back, and we have a brand new a battery with fresh life on the basis of salt. So it re-energizes the battery, and we use them for quite a while before it dies again. So that's chemistry good use of chemistry there. So later, when you have a solution of potassium nitride, the ions will actually dissolve to its distinguishing cation, or the distinguished cation and ions. So in this case, you have one molecule of K, which is there, and then another of an ion. The HNO3 is one negative. Don't be misled by this tree above. This is the subscript, and then the negative is the superscript. So you have one of the K and the NO3 one at the side. So this is almost like your sodium and your chlorine, but in this case you have a polyatomic anion and polyatomic anion here, and then your monoatomic cation. So this is what we call some form of conduction. And then we have another example here to construct this. So let me ask this question now. So how many molecules of potassium will you have? How many ions of potassium will you have? That's polyatomic cation. As you can see from the two. Then how many of sodium? Sodium sulfide. That's HO4. SO4. Sorry. It's just one because that's what you can see there. So it's going to be SO4 minus 2, or 2 minus. So that's why you have K2 plus to balance that, so that to be neutral. So obviously that's what it is. This is the solution. This is what it's going to look like. So you have more cation than anion. So we now go to the formulas of ionic compounds. Ionic compounds have formulas to themselves, talking about molecular formulas. So that's what we call balancing the charge. I just did that with potassium sulfide. Each positive charge must have a negative charge to balance it. So if you have calcium is group what again? As you can see, is 2. It's group 2. The only atom that doesn't work for, element that doesn't work for, is helium, because of the maximum number and the fact that after hydrogen, the next one is helium. You don't put it on the group 2, you put it on the noble gas because it's a noble gas. And we talked about the unique property of helium because of its nobility. And then you see chlorine, which is in group 7, and it needs one more electron. So notice that you have to have 2 chlorines to balance up the charge on calcium, because calcium is Cl minus. So you need another Cl minus so that you add the 2 minus to 2 plus, so it becomes 0. So it's going to be plus 2 minus 2, which is 0. So it requires 2 chlorine ion to balance the charge. So according to the principle of electrical neutrality, electricity, electrons, and then neutrality, neutral, for something to not be either positive or negative means that it's neutral. It has no charge. No charge means 0. So the total positive charge of cations in the formula must be equal to the total negative charge of anions. That's what causes the neutrality. When you have plus 2 minus 2, 0. Plus 1 minus 1, 0. Plus 3 minus 3, 0. So cations and anions with noble gas connections. Atoms that are close to noble gas form ions that contain the same number of electrons as the neighboring noble gas atom. So this principle can be used to determine the charges formed by the main group atoms. So look at this very closely. You have group 1, and the number of electrons is more than 1. noble gas, and the charge is +1. Examples is sodium and the potassium. So all of those group 1, they have 1 electron that if they give off, they take the noble gas conformation. And I told us previously that most of these atoms are striving to be as stable as noble gases, because noble gases are stable. So they tend to pursue that stability. So the way they attain that stability is by giving off their extra electrons and becoming like the noble gas, or collecting an electron and becoming like the noble gas. So it's very important that we understand that every student is trying to either give or take in the exam conditions to pass all of the exams in the first year, second year, third year, fourth year, and graduate if you're doing a 4-year course, then a 5-year course, and graduate, and then attain stability in your life so that you become noble, become respectful, and you have some money in your pocket to cater for your future and your family that have invested in you. So it's almost like the same idea with these things that we have around us. So you have 2 means a group 2, and it has 2 more than the noble gas, so it will give 2 to attain noble gas conformation. And you have examples because it's +2. You have magnesium, you have calcium that we saw previously, and then the ones that are 16 and 17. 16 now we receive 2 to now attain noble gas, so it has 2 less than noble gas, -2, and it has oxygen and sulfur. 17, which are your halogens, they have 1 less, so they will receive 1, and that's why you see sodium on top, and then you see calcium beneath, so they react to themselves, and then it gives you we see the electron neutrality, and then we see the balancing. So you have cations of transition and post-transition metals. Remember, your transition metals are the 13 to, using our periodic table in this case, the 13 to 12. 13 to 12, that's 10 count. Sorry, not 13, 3 to 12. So it's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 10 transition points. And then you have the post-transition, which is your 13, 14, 15. So post-transition. So metals are located further from noble gases in the periodic table form positive ions, and then transition metals in 3 to 12, as I said. Sorry, not 13 to 12. If you've taken that before, it's from 3 to 12, and then the post-transition from 3 to 15. And then many post-transition metals form more than 1 cations. So you have a situation where they can form more on the basis of that transitionality that they have going on for themselves. So an example is ion. You can have ion 2, you can have ion 3, and there's another interesting characteristics that you have to look out for when you are seeing, and that's why electrical neutrality comes in handy, where you can be able to see that you have 2 chlorine, so it should probably be 2 cations to balance up the 2 anion. Or if you have 3 chlorine, it should be, because chlorine doesn't have the ability to have multiple cations, so it's ion that has that on the basis of its metallic properties, that is transitory. So you have the polyatomic ions. We have only 2 common polyatomic ions. That's the ammonium and polyatomic cations. That's a positively charged polyatomic ion. So you have ammonium and then you have mercury. They are the only 2 and then you have several anions. You have them. See the table containing the most common polyatomic anions. You have everything as ammonium hydroxide, nitrate, chloride, hypochlorite, cyanide, acetate, manganese, hydrogen carbonate, dihydrogen phosphate, carbonate, sulfide, chromate, dichromate, hydrogen phosphate, and then the phosphate. You have all of these, the ones that have -1, -2, and -3. So you have them there. So they say predict the formula of the ionic compound formed by barium with iodine. So predict it. What's the number of subscript? Write the letter. So barium, what's the letter for barium? And what's the letter for iodine? Think of that first, and then you write the numbers underneath it. Notice it's going to be barium first, and then you have iodine. So write the number of the subscript. If barium will need more than 1, you write it. If iodine will need more than 1. I notice that I'm calling chlorine instead of iodine because they are this part of the same family. Fluorine, chlorine, bromine, all of those things. I'm calling them bromides. Chlorine, fluorine, bromine, iodine. So all of them are the same family. I'm waiting for you to write the formula. Predict the formula. So actually, barium is group 2. So it's Ba, as you can see, and then iodine is group 17. So it means that what you have is you need 2 of iodine to balance up the barium, the 2 of barium, and then you have Ba(I)2. Electrical neutrality. So writing the formula requires the knowledge of the symbol of the elements. Very important. So note that the symbols that are being used, you have to consistently try to remember them. So the symbols and the charges of the polyatomic are also needed. So those are the ones that the polyatomic ions, you need them so that you know the number of charges and easily connect them to the probably metal or the non-metal. I think mostly metal that's at the side that you need to add them to. Like SO4, you know that it's -2. So if you have a problem noting what is in front, if it's -2, you know that whatever it is that is in front has to have +2 to balance up for it to be a compound. So I think we'll stop here for this part and finish off. And next, this is part 3. So see you guys on part 4. Bye for now.